All right. The Cartesian equation of a line. Well, we're going to do the symmetric and the normal equation of a line, and then we'll get to the Cartesian. Turns out you already know the Cartesian. All right. So from the last lesson, parametric equation of a line, right? We have basically the x component and then the y component. Well, we solve for t, right? Solve for t, and what you have from each equation has to be equal because they're both equal to t, and that's called the symmetric equation of the line. We don't usually bother including the t, we just write it like that. All right. Yeah, there it is. Okay. Convert the vector equation or parametric equations to the symmetric equation. So we solve for t. So we have x plus 3 over 2 is equal to t, and y over negative 5 is equal to t. So x plus 3 over 2 is equal to negative y over 5. And there is the symmetric equation for that line. All right. So it's x over 1 is equal to y minus 1 over negative 2. Again, you can write it parametrically first, or you can just do it, I guess. Here, symmetric equation. We're going to have a problem, right? It's going to be x plus 2 over 2, y minus 3 over, oh, there's the problem, isn't it? So what does that mean? Well, uy is equal to 0. That means the line won't have a changing y value. What kind of line is that? It's a horizontal line. Okay. And so the symmetric equation doesn't exist. It does not exist, okay, for a horizontal line. It'll be the same problem for a vertical line. All right, because then the ux would be that ux would be 0 and be divided by 0 again. Okay, now example 2. Convert the symmetric equation of a line to the vector equation. Well, if you're not sure what to do, you can always set it equal to t, both parts, and then solve for x and y. That's really what's involved. So this will be x is equal to negative 2 minus t, and y will be equal to 3 plus 2t. Then to get the vector equation, the r naught is the negative 2, the y naught's the 3, the parameter is t, the x component for the u vector, the direction vector is negative 1, and for the y component it is 2. All right, so that is symmetric vector and parametric equations of a line connected. Normal equation. Okay, so you can see in green right here, we have a normal. And the idea is that it's perpendicular to u, to p naught and p, and r minus r naught. It's perpendicular to the line. The normal, remember the idea of negative reciprocal for slopes. For the direction vector means you change the x and y component and make either the y component or the x component negative, right? There's the y component negative, there's the x component negative. So that becomes perpendicular to u, right? If they're perpendicular to u, they're perpendicular to the line. Okay. So if x and y are some generic point, so if x and y are some generic point in the line, then p naught to p, where p naught's a reference point on the line, is parallel to u, of course, and p naught p is perpendicular to n, and p naught p dot n has to be equal to 0, right? Definition of dot product. P naught p is r minus r naught, so r naught minus r naught dot n equal to 0, right? That is called the normal equation of the line. Cartesian equation of the line. You take the normal equation and you plug in for n, well, okay, you distribute it, right? You dot it, r times n and minus r naught times n. And what you do is for the normal, you put components A and B. So those are the normal components. Then you have AX plus BY when you dot the first part, and you have negative AX naught minus BY naught from the second part. We combine these, which are a constant, to form C, right? I mean, that's what they're saying there. And that's the Cartesian equation of a line. Probably called it standard form in grade 9. Okay. The key thing is that the coefficient of x and y are the normal components of the normal vector. Okay. And c depends on a specific point of the line. It has to do with what x naught, y naught are. Okay. So if you take x naught, y naught, or r naught, and dot that with AB, you get C. But I don't usually do it that way, and we're going to do an example here, and you can see how we usually find C. Anyways, convert the vector of the equation of the line to the normal. So just to make it really clear, the direction vector is this. So the normal, we have to switch and make one positive. I see that the y is negative, so I'll make it positive. That way my normal is positive. And remember that we have this, right? Well, A and B are the normal components, right? The x and y components of the normal. So this is 2x plus 3y plus c is equal to 0. How do we get c? We substitute in a point on the line. So sub in a point in the line. Which point? Well, r naught takes you to a point in the line, so we're going to sub in r naught. 2 times 1 plus 3 times 2 plus c is equal to 0. That is 8 plus c, so c is equal to negative 8. So our line is 2x plus 3y, which we had before, minus c, plus c, so minus 8 is equal to 0. Cartesian equation of the line. Convert the Cartesian to the parametric equations and then to the vector equation. Well, there's sort of two approaches. You can get the direction vector, and here it is 2 and 1, for example. And then you can just get any point on the line, and that'll work. There's a sort of a cool way of doing it that, comes in handy when things get more complicated beyond this. You could just for example, let y equal t, then negative x plus 2t plus 3 is equal to 0. And x is equal to, bringing it over, right? But I flip-flopped it right there. What I really have is the parametric equations, right? And now to get the vector equation, well, I'll write that underneath. To get the vector equation, 3 and 0 plus t, 2 and 1. That works. You could also let x equal s, let's say, and do the same sorts of thing. But one way of doing it is all you need. Connecting slope-intercept form. Okay. What we have here is solve the symmetric equation of a line for y. So multiply both sides by uy, so you end up with it over here. And then you add y naught. Okay, and look at that. That's slope. And I think I talked to you guys about that in a previous lesson. There's the slope, and that complicated thing is the y-intercept. Okay, what it really is it moves you from x naught, y naught along the line till you get to x is equal to 0. That's the idea anyways. Slope-intercept equation. Slope y-intercept equation, right? Not a lot to say here. I already talked about that. Convert the vector equation to slope y-intercept form. So just to be really clear, u is equal to 1, negative 2. So the slope is uy over ux. So it's just negative 2 over 1 or negative 2. That's the slope. Now you can try to do something more complicated and find t when x is 0, but I would think you would just go like this. M, so it's this. And since grade 9, how do you find b? You're trying to get the equation of the line. If you already have slope, you sub in a point. So we need a point on the line, -2 and 3. So I would do 3, -2, x is -2 plus b. B is equal to -1. So y is equal to -2x minus 1. That wouldn't be too hard to find when x is 0, the t value there. But anyways, that's the way I would normally think people would do it. Example 6, convert the slope y-intercept equation of the line to the vector equation. Slope is -2 over 3. Remember, then that's uy over ux. So the vector equation, the direction vector for the line would be 3 and -2. I need a point on the line, right? P naught. Well, I can just use the y-intercept, 0 and 4. So then R is R naught. R naught is OP naught, so 0 and 4 plus T, 3, -2. And there's the equation of line in vector form. Angle between two vectors. And there's something added in here. I don't think it's in your notes, so make sure you add that in. You can either find use the dot product to find the angle between the two direction vectors, right? Dot product, solve for cos theta, and then get theta. Or you could use the normals. So if you have them in Cartesian form, you can use the normals. Or if you have it in vector form, you can use or parametric form, you can use the direction vectors in the dot product. And there's just a thing to illustrate it. I didn't want to clutter it up with the normals. You will always find them when they are tail to tail. So if you ask for the acute vector and you do this and somehow you get an obtuse vector, it's just the supplement of it, of course. Find the acute angle between each pair of lines. Okay, I have vector equation for line 1. So I have u1 is 1 and -3. I have symmetric, which isn't that convenient, but it's not bad. The direction components are 3 and -2. Cosine theta is u1 dot u2 over mag u1 mag u2, right? So first thing I'll do off to the side here is dot them. So 1 and -3 dotted with 3 and -2. That's 3 plus 6 or 9. Magnitude of u1 is 1 squared plus -3 squared. That's root 10. Magnitude of u2 then is root of 3 squared plus -2 squared is root of 13. So cos theta will be 9 over root 10, root 13. And you grab your calculator and you inverse cos, and you get theta, 37.87 degrees. Okay. All right. Find the acute angle between each pairs of lines. This is in Cartesian form. This is in slope, y-intercept form. So I can change both of them to u, or just change m to normal. So I'll do that. The direction vector then is 3 and -1. Then the normal, this is for normal 2, change the order, change one sign. So that was normal 1, cosine theta is normal 1 dotted with normal 2, mag of normal 1, magnitude of normal 2. You dot the two of them out, you get -7. Magnitude of normal 1, that is 13. Magnitude of normal 2, that is 10. Theta is 127.87. Said to find the acute angle, so I guess I'll find the supplement. 52.13 degrees. There's the angle between line 1 and line 2. Parallel and perpendicular lines. So this is an additional example, example 8. Something got garbled there, so I hand wrote it out. The two lines are parallel if the normals are scalar multiples of each other. And they're perpendicular if the normals are dotted out with each other. Of course, the same can be true for the direction vectors. Okay, if they dot to each other and give you 0, if they're scalar multiples, if they're parallel or perpendicular. Are lines 1 and line 2 parallel? Well, U1 is 2, -3. And U2 is 8 and -12. Well, is there a K that exists? Can you find a scalar multiple that exists? Sorry, those aren't U's. Those are N's. Normal 1 and normal 2. Is there one that exists? So it looks like for the X, 1/4 would work, and that would work for both. K is equal to 1/4. So normal 1 is 1/4 of normal 2. Normal 2. Therefore, line 1 is parallel to line 2. Since the normals are parallel, then they are parallel. Yeah, they're not the same line. If you look at the C, they're not. They don't line up. Find K so that line 1 are perpendicular. So we have normal 1, 2 and K. Normal 2 is 3 and 4. We need to find the value of K so that they're perpendicular. It means the dot product is 0. So we have 6 plus 4K is equal to 0. K is equal to -6 over 4. K is equal to -3 halves. If K is -3 halves, then they are perpendicular to each other. All right. And that's it for the lesson.